Okay, that's the basics, but let's just very quickly look at this very last slide from chapter 13. So chapter 13 is all about equilibrium, how things can shift back and forth. And I mentioned briefly Le Chatelier's principle. And that's this idea that when you have, actually, let me sign in for Zoom, my desktop as well. Otherwise, I can't see you guys' comments and stuff. Or actually, because we're doing it all on Zoom, you can ask questions with audio as well. Feel free to just interrupt me at any point. So when a reaction system's at equilibrium, the forward and reverse reaction rates are the same. So we talked about a few different things that can change those reaction rates. One of those was concentration. Oops. Right up here. So if we increase concentration, then we increase our reaction rate in the direction away from where we increase the concentration. So for example, on these problems, or in this example here, we have some system that's at equilibrium. And if we imagine that this is water in here, and we add extra water to tank A, that water is going to want to flow over to tank B to level out. And so we'll eventually reach equilibrium again, but at a new sort of water level. So the questions involved here would be, what happens, or which direction does the equation shift if we add, water to tank A? So in this example, if we add water to tank A, then the reaction shifts to the right or towards the products. If we instead had added water to tank B, then the reaction would shift to the left or towards the reactants. So for this reaction here, we have hydrogen reacting with iodine to form hydroiodic acid. If we add more hydrogen to this reaction, then this reaction will shift to the right towards the products. And if we add more hydroiodic acid to this sort of reaction equilibrium, then it'll shift back towards the left. And what else did we have that could change? Shift a reaction. I think for this class, it's mostly adding more.
But is it safe to assume that if you remove some from one to do the same thing?
Yes. Yeah.
All right.
So if you remove some, you're right. Yeah. So if we removed hydroiodic acid, then this reaction would shift towards the right. Yeah, to balance out that equilibrium again. And if you think about it in terms of rates of reaction, right, there's some forward reaction and there's some backwards reaction, forward reaction, backward reaction. And that rate is dependent on the concentration. So yeah, if we remove some of the hydroiodic acid, then our concentration goes down. If we remove HI, then concentration goes down, and the reaction, I should say not necessarily the reaction, but the equilibrium would shift towards products. because we didn't really talk about for like exothermic reactions and endothermic reactions and changing the amount, changing the temperature, because in those reactions, temperature acts kind of like one of the reactants, one of the products, but we didn't talk about that. That's something you talk about in Chem 20. Okay, so that's it for chapter 13. Are there any typed questions? All right.
Professor K.
Yeah.
Do you have any slides that we can print out for this chapter 14? Because it only goes to chapter 13 on the pages.
Yeah, I realized that this morning. I just expected there to be slides already made for this, but they're not. I will, I can send out these Chem 20 slides right now.
Okay. Thank you.
Mm-hmm. Let's see. I'll add it to the lecture resources page. Which I also need to add chapter 13 to. This is actually the last chapter. Chapter 14 is the last chapter. Almost there. Good slides. Did it upload? There it is. Okay, the chapter 14 lecture slides are there on the lecture resources page on campus. Okay. So acids and bases, you hear about acids and, vat of acid and like James Bond movies and stuff. They drop things in and they completely dissolve. You really hear about bases as much in any sort of pop culture reference. There are some acids that will act like that. Hydrofluoric acid is one of them. But acids are very, very common, and they're in a lot of foods. So citric acid, for example, is found in lemons and limes. Acetic acid is present in vinegar. And tartaric acid is one of the acids used to coat Sour Patch Kids. Because acids in general are sour. So acids combined with the saliva on your mouth and produce H plus ions or hydronium ions. And those H plus ions react with protein molecules on your tongue and send an electrical signal or nerve impulse to your brain that you experience as a sour taste. I believe Hank Green had a TikTok where he was talking about how you can taste protons. This is what he was talking about. So some properties of acids. Acids have a sour taste. Acids dissolve many metals. And acids will turn blue litmus paper red. So litmus paper is one of the ways that or is that an indicator of how much acid or base is in a solution. So some of the common acids, we've talked about these, talked about naming these. So like hydrochloric acid, sulfuric acid, nitric acid, acetic acid. These are all things that are used sort of every day. Carbonic acid is actually how carbon dioxide dissolves in water, will form carbonic acid. Hydrochloric acid is used for metal cleaning, food preparation. Sulfuric acid, nitric acid are both fertilizers. And acetic acid is the active component of vinegar. These are all very common molecules. Bases, on the other hand, have a bitter taste, and bases have a slippery feel to them. Bases turn red litmus paper blue. I believe it's litmus paper that's actually comes from a lichen, which is like a type of symbiotic plant that grows on trees. It was one of the first indicators. Bases are really common in cleaning products. So all of these consumer products here, never heard of Fantastic. But the other ones you've probably heard of, Drano especially, is ammonium hydroxide, or not ammonium hydroxide, sodium hydroxide. Bases feel slippery because they react with oils on your skin to form soap-like substances. Bases are less common in foods. They are bitter. Caffeine, though, is a base. I don't know what conine is. A lot of alkaloids are organic bases found in plants, like hemlock, which are often poisonous. Their bitter taste warns us against eating them. And coffee is acidic overall, but bases such as caffeine impart a bitter flavor, along with other stuff in coffee. So some common bases: sodium hydroxide, which is used in petroleum processing or soap and plastic manufacturing. Does sodium hydroxide or potassium hydroxide is also lye, which you used to make like canned peaches. Potassium hydroxide used in cotton processing, electroplating, soap production. Sodium bicarbonate is a really common one, you've probably eaten before. It's used as an antacid, but it's also an ingredient of baking soda and a source of CO2. And then ammonia is all over the place, especially in detergents, fertilizer and explosive manufacturing, and synthetic fiber production. So that's usually the like cleaning product smell. If it's not bleach, it's ammonia. And you don't want to mix the two. Definitely don't mix the two. So there are a couple different definitions of acids and bases. And one of those is the Aurelius definition. Sorry, I also have the textbook open here, so I wanted to kind of check. Well, I guess you haven't, we haven't covered how to name acids and bases, because that's in this chapter. Okay. All right, well, before we get into that then, we'll take a little detour here. So I just want to add another page. Add another page, select another page. All right, quick little detour here for how to name acids and bases. So there's two basic types of acids and bases. The first is, and the simplest name, are binary acids. And those are acids, as the bi would suggest. They have two elements. So some examples would be HCl, HBr, HF, HI. In my periodic table, I'll come up with a few more of these. It's pretty much the really common ones, but at the very least. Excuse me. So the way that we name these, and you'll notice too that they all start with a hydrogen. And that's actually one of the ways that we can identify acids. So acids start with hydrogen. So when we name these, we had hydro as a prefix. And then we put the name of the non-hydrogen element, but we changed the ending to IC. Then we put acid at the end. So if we apply these to these examples, or apply this formula to these examples, then we have chlorine in this binary acid. We know it's a binary acid because there's two elements. One of the first one's hydrogen. So we have chlorine, so we're going to say hydro, and then we're going to start writing chlorine. But when we get to hydrochlor, we want to change ene to ic. So hydrochloric acid. So for bromine, all right, again, it's a binary acid because we have two elements, and the first one's hydrogen. So we're going to start with hydro, and then we're going to start writing bromine, but instead of saying bromine, it's hydrobromic acid. I'm trying to think of other examples. Like it really is fluorine, chlorine, bromine, iodine. Those are like the really common binary acids. I don't know if there are any other binary acids. There probably are. Just can't think of them at the moment. All right, so how would you name this next one, right? Binary acid with fluorine.
Hydrofluoric acid.
Yep. Hydrofluoric acid. Yeah. And this last one. Hydroiodic acid. I'm sure there's more. And in fact, I could just do a real quick Google search. We can see, let's see. Okay, well, but that didn't really give me a list. Okay. Oh, so one of them on this list that would, this one is generally called hydrogen sulfide, but I think that's more of a common name. Yeah, interesting. So again, we can name this though. So the common name for this one is hydrogen sulfide, but we can name it using our systematic name here. So it'd be hydro sulfuric acid. So that's really just sort of and I'll upload these as soon as we're done here, or this new set of slides with these annotations. Okay, so those are binary acids. The other type of acid that we have are called oxyacids. Let's see, talk about naming oxyacids? Hope so. Yes, okay. Oxyacids also start with hydrogen, just like our binary acids. But as the name would suggest, they all include oxygen. And more specifically, they're made up of polyatomic ions. And these are also named systematically, although the naming does get slightly more complicated because we can have varying numbers of oxygens. So let's see, HNO3. So when we're talking about oxyacids, you have to know something about the polyatomic ions. So let me actually back up a step here. If we have NO3 minus, this is nitrate. So it's nitrogen. But we've taken off this, the ogen ending there, and we've changed it to ATE. So all of the polyatomic ions have an ATE form. Whether that's 3 oxygens or 4 oxygens depends on the ion. And I can upload a guide for how to memorize those if you want to memorize them. I'm not going to test you on those specifically, but it's one of those things that is helpful to know. Actually, make a note of that real quick. It's helpful to know. Okay, so we can also have NO2 minus. This is nitrite. I think actually maybe you guys have covered this. So again, it's nitrogen as the non-oxygen atom here. And we've just changed this ending to ITE. And then we can go 1 oxygen further to NO minus. And this would be, oops, not only now would it be nitrite, but it is hyponitrite. So adding the hypo suffix or prefix along with the ITE suffix removes 2 oxygens from the base form. And we can actually go and add an extra oxygen and we can get pernitrate. So here we, right, because it's an ion, we're doing ATE, but we're also adding per to the front. So these rules for changing the suffix also affect the oxyacids and how we name them. So if we were to write these out as oxyacids, HNO3, actually, sorry, let me start at the top, HNO4. So we have pernitrate. And notice too that on each of these, the charge is the same. When you change the number of oxygens, it doesn't change the charge. So this would be pernitric acid. So when we're changing and naming oxyacids, if we have ATE, that changes to IC. Similar to the ending that we use for the binary acids, except for oxyacids, we don't also include the hydro. So there's no hydro for oxyacids. So if I was to give you a name, for example, nitric acid, or if you saw nitric acid on an exam, you would know that this is not a binary acid because it does not include hydro in front. And so here we're doing the same thing, ATE to IC, but we're leaving the per off. So that means that we have HNO3 as just the ATE form.
I'm sorry, I have a question.
Yeah.
Okay, so up at the top where you did NO4, is the correct way we should write that is per nitrate?
Yes.
And the other ones do not have per in front of it, correct?
Correct. Per means you're adding one oxygen.
Okay.
So yeah, when you if you take a look at that polyatomic ion guide, I use this NO3 as the base form, quote unquote. It varies from class to class. Some people use the ITE form as the base form. But basically I say memorize the ATE forms and then memorize the prefix and the suffix changes and how those affect the number of oxygens. Okay. So if you know that nitrate is NO3 and you know that per adds one oxygen, then you know per nitrate is NO4.
All right.
If you know that ITE removes one oxygen, then you know that nitrite is NO2 because it's one less oxygen than the base form ATE.
Right. Okay.
And then, then hypo removes one more.
Okay. All right, thank you.
Mm-hmm. So then this changes a little bit. If we change the ending of our acid, I don't know why it's giving me another page. Oh, actually, I know why it's giving me. Okay. So if we have per nitric acid, these both in their non-acid form end in ATE. But if we end in ITE, we need a different ending to signify that we're using that ITE ending. So if we have HNO2, that's now nitrous acid, OUS. So if we have ITE, that changes to OUS. And then if we have HNO, then we have hypo nitrous acid. So again, ITE going to OUS, and we just have the hypo on the beginning, and then up here we had per at the front. And this will apply to all of the oxyacids. So actually, if you're in chapter 14.1 of your book, table 14.1 is names of common acids. Okay. So, quick recap. Binary acids, we had hydro to the beginning, and we changed the ending to IC. There's really only a handful of these. For oxyacids, we do not add hydro. We just change the ending of the oxyanion to IC if it's ATE, or to OUS if it's ITE. All right. Back to these definitions of acids and bases. The Arrhenius definition of an acid is really just an acid. I should use red for acids. It produces hydrogen ions in aqueous solution. So trying to remember if we talked about net ionic equations, or there are these, well, HCl is a covalent compound, which does not contain ions. But when you add HCl to water, it ionizes, and it splits up into an H plus ion and a Cl minus ion. And so in solution, these ions will actually separate. And they'll be floating around separately in the solution. So because we're adding hydrogen ions to the solution, that is an acid by the Arrhenius definition. And hydrogen ions are highly reactive. So in aqueous solution, they'll bond to water molecules, and they'll form this, which would be an H3O plus ion, which is known as hydronium. In water, the hydrogen ions always associate with water molecules. They are never found alone. We often write, as chemists, we'll write H plus and H3O plus interchangeably to refer to a hydronium ion. But the correct way to, or the correct thinking about how it is in solution is H3O plus. It's just easier to write H plus sometimes. When writing the molecular formula for an acid, we usually write the ionizable hydrogen first. Oh, well, this is kind of what we were talking about previously. So we write the hydrogen in front. So that's why for each of those hydrogen atoms or hydrogen molecules, sorry, acid molecules, they all start with hydrogen because that tells us they're an acid. Then we have a structural formula that would show how they're bonded together. The molecular formula indicates the number. So molecular formula just indicates the number of each type of atom. Familiar with molecular formulas. Bases in the Arrhenius definition produce OH ions in aqueous solution. So sodium hydroxide, just like HCl, ionizes when it enters a solution and splits up into the separate ions down here on the right of sodium and hydroxide. So whenever we add sodium hydroxide to a solution, it splits up into those ions. There are other compounds, so molecular compounds containing an OH group, such as methanol, do not dissociate in solution and do not act as bases. So these will be ionic solutions. So we'll have a metal plus OH. Those will be bases. Under the Arrhenius definition, acids and bases naturally combine to form water. Right? If we take our hydrogen and we add it to a hydroxide, then we'll get H2O. The Arrhenius definition doesn't explain why some substances act as bases even though they do not contain OH minus. So under the Arrhenius definition, this is the acids have to combine with bases to form water. But we do have some molecules that can act as bases even though they don't have an OH minus. And then the Arrhenius definition can't apply to non-aqueous solvents. So if we added HCl to hexane or some other organic solvent, the Arrhenius definition doesn't have any way to decide if something's an acid or base, because it is based on adding your acid or your base and how they act in H2O. So the Bronsted-Lowry definition is a much broader definition of what an acid and a base is. And it simplifies things. An acid is a proton donor. Acid is a proton donor. A base is a proton acceptor. You might think, oh, what do you mean a proton? So hydrogen on the periodic table has one proton. And it has one electron. So if we have H plus, we've taken away that one electron, and so now it's just one proton. So in this Bronsted-Lowry definition, the proton that it's talking about is hydrogen, and specifically this hydronium ion or hydride. So this H plus is just a single proton. So looking at where that proton is coming from and where it's going lets us know if it's an acid or a base. HCl is a Bronsted-Lowry acid because in solution, it donates a proton to water. If we had HCl, right? It's still true that HCl, let's see where I write this. HCl, when added to water, let me write it like this. Well, yeah. So we take HCl and we add it to water, we get H plus Cl minus. But as we talked about a few slides ago, it's more correct to say that this H plus is actually being donated to water. As H plus being donated to water to give us the H3O plus. So it's an acid, HCl is an acid, because it's donating its proton. And then also by the Bronsted-Lowry definition of acids and bases, water here is a base because it accepts that proton. The Bronsted-Lowry definition also works with bases such as NH3 that do not contain OH minus ions, but still produce OH ions in solution. So when we add ammonia to a solution of water, the ammonia actually accepts a proton from water. So one of these hydrogens is being donated to ammonia to make ammonium. So ammonium, and then we're left with OH minus, which under our previous Arrhenius definition would be a base, but it doesn't have OH minus. So here, water is our acid because it's donating a proton, and ammonia is our base because it's accepting a proton. So acids and bases always occur together. If we have some acid, it has to donate a proton. And if it's going to donate a proton, there needs to be a proton acceptor. So for HCl, as I mentioned, HCl is the acid, water is the base. For ammonia, NH3, ammonia is the base, and water is the acid. Water is special because it is amphoteric, which means it can act as an acid or a base. So water can be either. So when the equation representing the Bronsted-Lowry acid-base behavior of ammonia is reversed, now we have NH4 plus, and that's our acid, because it will donate some protons to OH minus in solution, and we'll get ammonia again and water. So NH4 plus is not amphoteric. Amphoteric means water can either gain a hydrogen to become H3O plus, or it can lose a hydrogen to become OH minus. Here we just have ammonia, NH3, can only gain a proton to form NH4 plus, and NH4 plus can only lose a proton to become NH3. So amphoteric compound is one that from a single form can go one way or the other. This NH3, NH4 combination is known as a conjugate acid-base pair. So you'll notice that this is just our reaction from earlier reversed. And as we just talked about equilibrium, in equilibria, these things are in equilibrium with each other. So there's always going to be some NH4 acting as an acid. There's always going to be NH3 acting as a base. There's always going to be some water acting as an acid, and some OH minus acting as a base. And so these would be the conjugate. Actually, yeah. So in this reaction, on our product side, these are the conjugate base and the conjugate acid for this reaction. So conjugate acid-base pair is any two substances related to each other by the transfer of a proton can be considered a conjugate acid-base pair. So, right, one example is the NH3. Do it like this. And NH4 plus. You could even say that HCl and Cl minus, right, related by a transfer of a single proton. Or to go back to our example of an oxyanion, HNO3, NO3 minus. These are all conjugate acid-base pairs, all related by the single transfer of just a single proton. Oops. So a base accepts a proton and becomes a conjugate acid. An acid donates a proton and becomes a conjugate base. So here we flipped that reaction from a couple slides ago. Now we have NH3 as our base, and NH4 plus is the conjugate acid. The conjugate acid and the conjugate base are always going to be on the product side. Our acid and base will always be reactants. Okay. for these reactions, let's identify these acid-base pairs. So in this first one, got this C5H5N and H2O. And I think one of the easiest ways to identify what's going on is to say, okay, this is this on the reactant side. On the product side, it's gained a proton. And for water, water's lost a proton. So then a proton donor is an acid. So water lost a proton. So this is our acid. And if water is the acid, that means the C5H5N is our base. So the conjugate acid and conjugate base are just going to be the opposite of these on the product side. So if C5H5N is our base, on the product side, it's going to be our conjugate acid. And if OH minus, was if water was our acid over here, then the OH minus on the product side is going to be our conjugate base.
Sorry, I just want to ask, is it because we're working with acids that we're not putting that hydrogen with the other hydrogen to make it C5H6N? Or is that like an entirely, yeah, okay.
No, yeah, you're exactly right. That's exactly why we're not. Yeah, you don't want to put it in there, because if we put it in there, that'll make it look like it's, well, technically correct in terms of the structure. That would be like incorporating it into like the sort of more permanent structure of the molecule.
And not something that could like switch it back and forth.
Right. Easily switch back and forth. A phone call. Huh. Let me check something else. Okay. Yeah, so exactly. This gets tacked onto the end because it's not like a permanent part of the structure, and it's going to be, right, we have a two-way reaction arrow here. It's going to be flipping back and forth between these two forms in equilibrium. Okay. On this next one, we've got nitric acid. Oh, well, I guess that kind of gives it away. But looking at it here, we start with the hydrogen. On the product side, it no longer has a hydrogen. So that makes it the acid. Our water starts with 2 protons and gets a 3rd proton. So this is sort of an exception to what we were just talking about, where we tacked this onto the end. Water, in so many ways, has exceptions and is an exception. But because this gains the proton, this is the base. So then on the other side, we have our conjugate base and our conjugate acid. Is that all good? I can check the chat occasionally. Oops. Who's trying to? Okay. So for these acid-base reactions, if we're reacting an acid with a base, that is, you generally form water and an ionic compound or salt. So if we have HCl, hydrochloric acid, and potassium hydroxide, a base, then we end up combining hydrogen hydroxide to get our water, and then potassium and chlorine to get our potassium chloride salt. So the net ionic equation for many neutralization reactions, have you guys covered net ionic equations?
I don't know if we did. I don't think so.
Okay.
Yeah, me either.
Net ionic equations is in, oh, of course, it's, oh wait, no. Maybe we don't cover it. It's in like one of the questions for chapter 12, but it's not in chapter 12. So I'm not sure why that is. That's okay. If it wasn't in the other stuff, then you don't need to know it. So the reaction of acids with carbonates or bicarbonates. So we react acid with CO3 2- or HCO3-. We produce water, gaseous carbon dioxide, and a salt. It's also called a gas evolution reaction. So we mix two liquid solutions together to produce a gas, and that's a gas evolution reaction. You wouldn't technically think of like, if you burn something, so like if we had like CH4 plus O2 does produce CO2 gas plus H2O gas, don't generally think of that as a gas evolution reaction. It's usually these two liquids being mixed together. We don't have to worry about that much though. Don't worry about that for this class. So let's write a molecular equation for the reaction that occurs between HPO4. So this is another one of those oxyacids. So this would be the base form for PO4 3- is phosphate. So H3PO4 would be phosphoric acid. So we have our phosphoric acid, H3PO4, plus sodium hydroxide, and this is important to note. So if you notice that our base oxyacid here is PO4 3-. That means that all three of these hydrogens are acidic hydrogens. So they're all protons that can be donated. So then our product here will be our salt, which are going to be our Na3PO4, because PO3 has a 3- charge. Sodium has a 1+ charge. We're going to need 3 of those sodiums to balance the charge on phosphate, plus H2O. But we do need to balance this equation. So usually I start on the left, but I think hydrogen is going to be hard to balance. It might not be. Well, yeah, hydrogen is going to be hard to balance, and we don't want to balance it first because we have hydrogen here, and we have hydrogen here. So both of these hydrogens are going to be contributing to the H2O. How many hydrogens are in H2O? So you generally want to balance those kinds of things last. Phosphate is already balanced too. Plus, we don't want to change the number of hydrogens. So we balance sodium first. So Na and Na. So we need 3 sodiums. That's going to give us 3 oxygens. So I'm going to put 3 over here to balance the number of oxygens. And then I believe that balances our hydrogens as well. So if we have on the left side 6 hydrogens, because we have 3 here, plus 3 times the number of hydrogens there. So 6 hydrogens. We have 1 PO4. And then we have 3 Na. Oh, and the oxygens. We have 3, oops, random space, 3 oxygens. And then on the right side, we have 3 times 2 hydrogens. So that's 6 hydrogens. We have our 1 phosphate. And we have 3 sodiums. I guess I'll do oxygens on top, but we have 3 oxygens as well. So this would be the balanced chemical reaction. So it's really just identifying your acid and your base and knowing that you're going to be making a salt. So basically, so you're taking the non-hydrogen part of your acid and the non-hydroxide part of your base, and you combine them together into your salt. All right, so this goes there. And then the other 2 are going to be your protons, your hydrogens, and your hydroxide, which are going to form water. I'm not sure if I'll put a problem on there. It'll probably be more like, identify the acid, identify the base, identify the conjugate acid, conjugate base. What is the definition of an acid? Those will be the kinds of questions that I'll ask. Okay. So you're going to stop there. And we can get to the rest of this actually next week, because the exam is on Wednesday. But we have a little bit of time if you have any questions about the exam on Wednesday. No questions? I did last night. I guess I was wrong about what we were going to cover in lecture today, but I did last night send out a little sort of study guide. It's going to be a relatively short exam. It's just 15 questions. There will be some calculations that you have to do. And I've given you the table of, where was that in your book? I gave you this table where it gives you the number of electron groups, electron group geometry, bonded atoms, lone pairs, bond angle, molecular shape. Right, so you'll have to know how to draw a Lewis structure for one, and then also use the Lewis structure to determine the geometry of the atom or the molecule. 16 questions. 16 questions.
I had a question. I was practicing the Lewis dot structure thing that you posted.
Mm-hmm.
And I guess I'll go over it when I have the conference or the Zoom later. But I was just wondering, is there only one way to draw it? If you have the same amount of, I don't know, what, I have it, I guess, circled. I just was wondering, is there only the way you drew it for the key? Is that the only way to draw it?
Yeah, there should only be, so there are some there's some, let me go to just like a random note.
Like on SO2, so it has like 18 valence electrons.
Yeah.
Like different. Like I
Because
was
I think
wondering if I couldn't use 2 double bonds. Yeah, like that.
it should have 1 double bond.
But why can't you have 2? Aren't you supposed to try to reduce?
Because you're not, if you have 2 double bonds, then you're gonna have too many electrons.
Oh.
But this should have 18 total electrons. So it'd be 2, 4, 6, 8, 10, 12, 14, 16, 18. And then we only want these each to have 8 total electrons. So oxygen here has 2, 4, 6, 8. Sulfur has 2, 4, 6, 8. And oxygen has 2, 4, 6, and 8. So that would be balanced for that one. Because if you do 2 double bonds, then sulfur, because we'd have to take, or well, you could do it a couple ways. If we take a lone pair from oxygen and do this, now sulfur has 2, 4, 6, 8, 10 electrons, and that's exceeding the octet.
Oh, okay, because of the octet rule. Okay.
Yeah, so yeah, the number 1 rule for Lewis dot structures is the octet rule. There are some exceptions, of course. Hydrogen, boron. So hydrogen only gets 2 electrons. Boron only gets 6 electrons, and aluminum only gets 6 electrons.
Okay.
That's for this class. Outside of this class, there are other ones that have expanded octets, which if I posted the Lewis dot worksheet, there are like four of them on there that have expanded octets.
Right.
Yeah. And then you can also get into other ways to, there's other considerations that you make at like in classes, not even Chem 20, it'd be like Chem 1. You would start talking about this stuff. Other ways to draw Lewis dot structures and other considerations that you have to take, but we're not doing that for this class. For this class, it's all about the octet rule. So as long as every atom has the right number of electrons, usually 8, unless it's one of these 3, then you're good. That's where you stop.
Okay.
So then the only other way to draw this would be to flip it to the other oxygen.
Let's see here. 3. Oh, I see what you're doing. Okay. You could draw it that way though too, right?
Mm-hmm. And these are actually called resonance structures.
Okay.
Is there any other questions?
Sorry, just to clarify, the one with the 2 double bonds is wrong because then sodium has 10 electrons, right?
Sulfur, but yes.
So sulfur, right? Sorry.
Yeah, you're right. It has 10 electrons, so that's too many.
Alrighty, that's it for me. I'm still studying the list.
Yeah, go through that list. Those are like, yeah. I mean, you need to know stuff. For some of these problems, you do need to know like previous stuff because it's adding gas laws on top of other things. But yeah, hopefully this should be, I don't know. I don't want to set your expectations for what it's going to be or what it's not going to be. Okay, yeah, if there's no more questions, I'll post this video right now and those lecture slides and a guide for polyatomic ions, which is mostly just for your own study. So it's not going to be tested on specifically.
Okay.
All right. Again, sorry if any of you showed up to the classroom car trouble this morning. But it should be set, good to go on Wednesday. I'll be there Wednesday.
All right. Thank you.
All right. Thanks, everyone.